So we're going to go ahead and get started today. Our first speaker is Eric Williams. Eric Williams is a professor at the Golasano Institute of Sustainability at Rochester Institute of Technology. His research addresses the intersection of sustainability, technological progress, and social change. His talk today is titled "The Nonlinear Shift to Renewable Microgrids, Phase Transitions in Electricity Systems." Eric, you want to kick us off?
Sure. I'm going to share screens. Can everybody see my slides?
Looks great.
Okay. Yeah, these short form talks sort of feel like that Major General song in Pirates of Penzance. You know, I am the very model Major General, but I won't talk that fast. Hi. Heads up, this is published work. It came out a few months ago, and so I'll give the reference at the end of the talk. First off, I'd like to establish some common ground on the salient parts of phase transitions in physical systems for this talk. And so here is the phase diagram for water. The state of matter is determined by whether it's liquid, solid, gas, is determined by pressure and temperature, driving variables, so to speak. And there are sudden changes between the state for certain values of these driving variables. Another important feature of phase transitions is that the phase that a system is in is determined by the minimizing the free energy of the system. And then if you're looking at the free energy as a function of temperature, when you cross the phase, you'll see discontinuities in the free energy or the derivative of the free energy. So here, this is showing for a sample system, the derivative of Gibbs free energy is for temperature, pressure, we see discontinuities. And then for the Gibbs free energy itself as a function of temperature, we see it has a corner, which is reflective of those discontinuities. And so these are the main features of phase transitions that let's keep in mind for this talk. So the idea here now is to explore the formalization of and the ideas of their phase transitions in energy systems. And so now the driving variables would not be temperature, they'd be things like technology prices. And the state of the system isn't solid or liquid, it will be the composition, the presence or activity of different technologies, renewable, fossil, what have you. And so to illustrate the idea, here's an example where we're considering two variable technology prices, storage price and solar price. And imagine that solar price and battery price are very high. Then any least cost energy system will not incorporate them in the system, and the least cost system will be fossil fuels or something else. And then, but if you imagine really, really, really super cheap solar and batteries, then the least cost system will be just those two technologies, excluding everything else. And so it's like a phase transition. We have these regions where there's different compositions of technologies that there's switches between the as a function of driving variables. And what happens in between? Is this all smooth and linear? Is it nonlinear? Do we see phase transition kind of behavior? And that's the thing that we're going to explore, where now the state is the presence or activity of different technologies. So let's look into this idea with some modeling, build a phase diagram for a microgrid. And so solar and battery price are going to be the variables, analogous to temperature, pressure, or volume. We're going to find the least cost microgrid design for basically all possible prices of solar and batteries. And we'll look for nonlinear phase-like behavior as a function of technology costs. And by the way, we're starting with microgrids because they're designed and built in one go. Microgrids, I think this ideas are applicable to macrogrids, but the short answer is that they're non-equilibrium systems. We can talk more about that later, but let's just focus on microgrids for now. So methods, we pick a set of technologies. In this case, it'll be 3: diesel generator, solar batteries, a couple locations, a northerly and equatorial one, a couple of different demand patterns. And to find the optimal least cost system, we're going to use Homer Pro software. It's a standard in the microgrid world. And then we're going to run 79,000 different combinations of PV and battery prices. And you can imagine this took a little bit of computing time. So let's go straight to some results. This is what we're calling a categorical phase diagram. And so this means that the presence or absence of a technology is a phase. And so we have, for example, the red up here means that there's only diesel in the least cost system. And for high lithium battery cost and solar cost, that's what we see, because the system doesn't want to incorporate any of those. But then let's go to this bottom left-hand corner where you see it's orange. This is PV and storage, and there's no diesel left at all. It's a pure renewable system. And so for really, really cheap, we see that there was going to be a phase like in that conceptual diagram before of just the renewables. And then we see in between, we see regions that are very distinct according to different combinations. And we see that there are sudden jumps in between the presence, when a technology gets squeezed out, and some curious features like this nose thing, which we can talk about if there's time. So it's looking phase diagram-y-ish. Let's now continue with some more results, and that the cost of the energy system is clearly hugely important. And so we're going to show the levelized cost of energy of the microgrid as a function of these two technology costs. And we're going to show the equal distinct contours, the equal value contours. And so these numbers here are the constant LCOE in dollars per kilowatt hour. And I want to call your attention to the 0.1, that's 10 cents per kilowatt hour. The microgrid world is interested in this idea of grid parity when microgrids become of similar cost to a macrogrid. And so this reaching grid parity is a big deal in that space. And so we see here, this is now a functional relationship between PV and solar costs, PV and battery costs that you have to achieve in order to get to that cost goal. So it's not that, it depends. You can have cheaper solar and pretty cheap batteries, or even cheaper batteries and cheap solar, and different combinations. And also we've plotted here, this is the historical prices of solar and storage as would be implemented in microgrid. And we see that over the last decade, we've really moved through the phase space a lot, that's thumbs up. On the other hand, I think it's really interesting how the distance between these different years is getting smaller and smaller, which is showing a deceleration of price reductions. And so it's kind of like you're running, you keep slowing down. You keep running, but as you keep running, you're starting to slow down because you're decelerating, because it's essentially this. You see this in lots of technologies. Moving on, whoops, there we go. So now let's look at this discontinuity idea. And so now the analogy of minimizing Gibbs free energy is now we're minimizing LCOE. And so what's showing here is the LCOE as a function of solar price along the diagonal line where solar price equals storage price. And then as we go down in price, we see these corners, we see these discontinuities like in physical phase transitions. And what's interesting here is that the slope gets taller the more you get towards this goal of low costs. So in some ways, it's like as you're going, you want to reach the bottom of the hill, and the hill gets steeper as you go down, as you get further. And so that makes it easier to achieve this LCA reduction for a given reduction in the solar price. So that's positive. But on the other hand, remember on the previous slide, it's getting harder and harder. You're getting tighter and tighter as you get toward the bottom of the hill. And so what's the outcome is depending on the combination of those two things. So interpretation, so first I'll talk about modeling from modeler's perspective. I was trained in physics. For me, I love this, that there's this analogy between energy systems and physical systems. Why should we see this? I don't have a good answer for that. I have a few thoughts, but if somebody has ideas on why there are these fundamental similarities, I'd love to hear them. Let's jump right on into trying to talk a bit about the so what question, which any sustainability research has to address, or should address. And one is this grid parity question for microgrids, which is a community that's interested in it. And we're not giving an answer, but we're saying the actual answer is hard to predict for a new reason. I mean, it's this competition. It's a Zeno-style paradox between the hill getting easier to run down, but then getting tighter and tighter. And you have to understand the dynamics if you're going to understand the grid parity, which people haven't really, I think, looked at it that way. Policy, Department of Energy, often uses text targets, and other agencies use tech targets, price targets in the future as to inform R&D programs. And typically these price targets are set by technology. Like we want to have solar power be $1 per watt by 2030. What this is illustrating is that the energy system is a combination of technologies, and so it can be useful to think about combinations of price targets rather than stovepipe technology. This is exploratory work. Lots more to do. in particular, really interested in the generalization of microgrids because most electricity is made by macrogrids than mini grids, microgrids. But that's work in progress. I have something to say about it if there's time for it in Q&A. So thank you for attention, and here is the paper and the funders.
Perfect. Very interesting work. Thanks for that talk, Eric. One thing I forgot to mention at the beginning of this session is that each presentation will be 10 minutes followed by 5 minutes of Q&A. So do we have any questions from the audience? If you do, I think this is a small enough group. Go ahead and unmute yourself and go ahead and ask Eric your question.
You might
Daniel, go ahead. Yep.
Yeah. So Eric, I may have missed it at the beginning. So really interesting talk. What was the fundamental model that you were using here? I couldn't tell if there was an actual power system model in here, or can you maybe just say a touch
more? Yeah, I wasn't, because of the time limitation, of course, like what do I have to say versus not say?
Yeah, no, and that's probably what the Q&A is for, right?
Yeah. So
expand on what you didn't get a chance to expand on.
Yeah, and so basically it's a power system model for a microgrid that's simulated using this software package called Homer Pro, which is really a software package all about microgrid design. And so then they have, for each technology block, be it a battery or a solar panel, they have all the things in it, the lifespan and the power, the IV curves and everything. And so basically we're just using that software package. And we're saying, hey, here's the solar price, here's the storage price. You, Homer Pro, the experts, tell us what that system looks like, and also what the generations of all those technologies are. Is that enough? Does that help?
I think so. Yeah. I mean, so essentially, you might get different results with a different model, but
sure.
It's interesting just to notice the phase. So don't take maybe the literal boundaries too seriously, but just the existence of boundaries is what's really cool.
Correct. Yeah. So for our purposes, I mean, well, the tool, I mean, how do you validate these tools, right? And this is in terms, if you look at social validation, Homer Pro is the tool, the most primarily used tool in this area. And it's been around for a long time. So from that view, it's a good model, power system model of a microgrid. We actually, for this purpose, we don't really care, because we want to show the existence of these phase boundaries rather than, and we, whether it's at a particular place or not,
Thanks.
Can I ask a quick one?
Go ahead.
Yeah. So I'm just sort of curious. So you're talking about sort of chasing, I think you said grid parity, or
yes,
where your microsystems are hopefully approaching these macro systems.
Yes.
I'm sort of wondering, like, if the cost of the macro system is kind of running away, or if these microgrids are catching up.
I think there tends to be a catching up effect, because the technologies that you would make a microgrid with, the renewable technologies, are reducing it. They're reducing in cost much more quickly than, for example, natural gas or coal, these established grid technologies. And the thing is the grid can take on those technologies as well, but the grid is so slow to react, right? It's like little bit by little bit. But the microgrid just like boom, you tell me what the technology is now, and I'm going to build the cheapest thing now, and they can more easily incorporate the new cheap renewables. And so I think you see microgrids they're catching up, but they haven't caught up yet. And will they or not is still. Does that help?
Yeah. Thank you.
Michael, do you have one last question for us?
Yeah, Eric, I was just thinking about the turns in your lines. Is there lumpiness in the investments besides from the diesel genset? Like, is there any sort of, once your PV reaches this cost, the inverter has a large jump instead of a small jump?
Yeah, we consider we actually ignore inverter cost. And so there's simplifications that we make, and we ignore that, and the lumps of PV and the lumps of batteries are very small. Really, the only big thing is the diesel generator. Does that help? Yeah, you're right. With having the sizing of the inverter thing just turned out to, we decided that that it was better not to include that.
Yeah, I have a question, if I may allow.
Yeah, one last question.
Do you have any ideas what's going to be the impact of locations and solar radiations? I see the interesting selection of locations in New York and somewhere in other country. So any reason behind selecting these two areas and have any impact on the result?
Yeah, absolutely.
The same. Yeah.
Yeah, so qualitatively look very similar, but the thing is we chose these different locations because obviously solar is going to be more favorable in sunny places, and equatorial places tend to have more even solar, so you don't have to worry so much as the difference between summer and winter. And so the reason we chose Rochester, Mogadishu is that we wanted something up north where you have to worry a lot about the seasonality, and then south near the equator where you have more sun, more and even equal sun. And so what you see is that the size of this nose, if you think of this yellow thing as a nose, right? The nose gets bigger. The nose is a lot bigger in Mogadishu. And that's because of the improved conditions for solar. And so you're at the same technology cost, you're incorporating a lot more solar. It's much more sooner you can incorporate solar into the system. And does that answer the question?
Yep. Yeah, that's perfect. Yeah, thank you.
Perfect. Thank you, Eric. That was a very interesting talk. We'll move on to our next speaker now, who is Elise Lagace. Did I pronounce that right, Elise?
Lagace. That's good enough.
Lagace.
Yeah.
All right. Elise's talk is titled Assessing the Impact of Climate Change on Electricity Planning in Ontario, Canada. Elise graduated from Queen's University in 2016 with a bachelor's in chemical engineering. After graduating, she worked for Ontario Power Generation at the Darlington Nuclear Generating Station as a design team leader. She's currently pursuing a master's in civil engineering from the University of Toronto, researching the impact of climate change on current and emerging energy technologies. Elise, it's all yours.
Thanks. And as Branden mentioned, the title of my research here is Assessing the Impact of Climate Change on Electricity Planning in Ontario. As you all know, our climate is changing. Canada is continuing to get warmer. Winter precipitations are expected to increase, while summer rainfall will reduce for parts of southern Canada. Extreme hot temperatures will become more frequent and more intense, meaning an increase in heat wave severity and droughts. We are expecting higher winter water flows and smaller snowpack, all in turn causing lower summer flows in parts of Canada. So what does this mean for Ontario's power system? Temperature and precipitation are the main variables that have an impact on electricity generation. So looking first at the impact of increasing temperature, thermal plants require cooling water and cooling air, and due to the increase in temperature, the ability to cool will reduce, in turn reducing their efficiency. Solar panels are also less efficient at higher temperatures, and more extreme temperatures may also cause an increase in forced outages, further reducing our supply. Demand for electricity, on the other hand, will go up mainly due to air conditioning, increased air conditioning. Looking at precipitation and shifting stream flow. So in Ontario, we have a limited water reservoir capacity and a large river system to manage. So as I mentioned, the shift in stream flow may affect the availability of water for hydroelectric generation and cause forced outages or mandatory spilling at high flow to avoid flooding. So this is relevant because of the high reliance on hydropower in Ontario. Before going further into the impacts, let's look at Ontario's energy mix. So Ontario gets 23% of its capacity from hydroelectric plants and 13% from wind and solar. Thermal plants that convert heat energy into electricity, typically by heating steam to drive a turbine. So as I mentioned, these are highlighted here and make up approximately 64% of Ontario's mix. That means at least 87% of our electricity here in Ontario, all but wind power, could be impacted in a predictable way by changing temperature and precipitation. So are we planning appropriately for this? The current practice for measuring the reliability of the power system falls on the Independent Electricity System Operator, or the IESO. One of their goals is to maintain an adequate reserve margin to make sure that there is always enough electricity available. And reserve margin is defined as the effective capacity minus peak demand, or in short, supply minus demand. The main way resource adequacy is measured is through this loss of load expectation, or LOLE. It is defined as the average number of days per year where supply is insufficient to meet demand. So power authorities have to meet a certain LOLE reliability standard of less than 0.1 days per year, or 1 day every 10 years. The IESO calculates this annually with a probabilistic assessment using historical weather data, and currently does not account for the scope of climate change. There is a growing body of literature on how climate change might affect electricity, the power systems. Most studies focus on the impact to one component of the system. Because of the interconnected nature of the power system, impacts on multiple components, although small, might have a compounding effect. Many studies use the average from climate models and don't look at the hourly or monthly timescale, and this inherently hides the effect of extreme events and makes the results unhelpful for power system planning. On the other hand, power authorities who do the planning do not currently account for climate change in their assessments, as we saw with the IESO. So because our future will probably exceed historical extremes, our current calculations may be overestimating our ability to meet future energy needs. I therefore wanted to answer the following question: how does climate change impact Ontario's reserve margin and the resulting loss of load expectation? As we know, our dependence on electricity is growing. It is therefore super important that we ensure we have a reliable supply in our changing future. So to answer the question, first we have to quantify the impact of climate change on supply and demand in Ontario. So for this presentation, I'll focus on the results for 2040. To calculate the loss of load expectation, we had to model the supply and demand for every hour in the year 2040. So the first thing we needed is our future climate. We used our own climate model, a version of a community Earth system model that is regionally refined for a higher resolution in Ontario under the most pessimistic RCP 8.5 emission scenario. And this scenario selected to bound the problem. Out of this model, we get precipitation, temperature, humidity, which are used in supply and demand models I will now describe. So for demand, we use a piecewise temperature regression, which includes time-fixed effects to define the relationship between future temperature and electricity demand in Ontario. To model forced outages, we use a logistic regression to determine the probability that a generator would become unavailable, and vice versa, based on electricity demand, temperature, and humidity. And once we know if a particular generator is available, we then estimate the maximum amount of electricity it is able to produce that hour with a linear regression based on climate variables relevant to that specific generator fuel type. Forecasts for wind and solar radiation are highly uncertain. Therefore, we based our model availability for wind and solar on historical contributions to the grid for that monthly hour. Solar capacity is then corrected for the increase in temperature. The difference between the maximum effective capacity and the demand estimated here give us the reserve margin. And if this value is negative for a particular hour, this is a loss of load. So from performing multiple iterations for every hour in the year, we can calculate this loss of load probability for each hour, and from there, the yearly loss of load expectation. So we ran the model twice for the year 2040. And once as a control scenario, and again as our 2040 prediction. Both scenarios have the same 2040 baseline demand and capacity, but the control scenario uses 2018 weather, and the 2040 prediction uses predicted climate from our climate change model. These can be considered a non-climate change scenario versus a climate change scenario. Now jumping into the results. We see that hydro capacity goes up due to increased precipitation in our climate model in the summer, and gas capacity is reduced compared to the non-climate change scenario. Other fuels were not significantly impacted. Of the thermal plants, including gas, the impact varies based on the cooling technology. The highest negative impact is dry cooling, which relies on air temperature to dissipate heat. And these results align with some of the other losses of efficiency found in other studies. This is a time series of 2040 with no climate change. The y-axis is capacity and demand in megawatts, and the top line represents effective capacity, while the bottom line represents demand. We use a Monte Carlo simulation to produce the multiple iterations for every hour. And as shown by the legend in the upper right corner, the thick middle line is the average across all Monte Carlo runs per day. The shaded area includes the variation across the Monte Carlo iterations and the daily variation at a 90% confidence interval. Here, supply and demand follow that typical seasonal trend, and demand does not exceed capacity at this confidence interval. So now I'll layer in the climate change scenario. So the red line here illustrates the effective capacity with climate change. As you can see, capacity dips during the summer as expected, but remains almost consistent with non-climate change capacity in the winter due to milder winters. It has a much greater variability as seen with the larger shaded area due to climate variance and more extreme weather events. I've added the demand with climate change in blue, but for clarity, let me remove the control scenario. So here is just the climate change scenario. As we see here, capacity dips in the summer months while demand spikes at the same time. The wave shape for demand is consistent with that V-shaped relationship between demand and temperature. We believe the trends shown here, but as you can see, we don't read too much into the specific patterns. We currently have a limited number of iterations at this time, introducing a bit of noise in the results. However, we do believe it is reasonable to see some demand exceeding supply, as circled in black, which indicate a high loss of load probability. Moving on to some values. So we have the control scenario without climate change on the left and the predicted with climate change on the right. So the difference between the two scenarios really represents the impact of climate change specifically. The first values here are a numerical representation of what we saw in the time series. We have a higher peak and a lower effective capacity with climate change, resulting in a negative reserve margin. Moving on to the adequacy metric from our power system. So loss of load expectation, again, represents the number of days with a loss of load event, or the frequency. And the loss of load hour, or LOLH, is the total number of hours with a loss of load event, or the magnitude of the issue. As you can see from both LOLE and LOLH, climate change introduces more loss of load events in 2040. And just as a reminder, the adequacy standard states that the LOLE should be less than 0.1. So even our control scenario predicts an inadequate grid, but this is consistent with what the ISO is predicting already, a deficit in 2040. The additional effective capacity required to achieve the LOLE standard is about 5,300 megawatts. This is significantly larger than the effective capacity projected in 2040 with non-climate change scenarios and what the ISO is currently estimating. The additional capacity requirement projected here is equivalent to adding 2 more generators the size of OPG's Darlington nuclear plant. So climate change does introduce enough variability in the calculation to affect the adequacy results. This means there could be a need for additional capacity that we currently don't have connected to the grid or significantly more imports. To conclude my presentation, I wanted to acknowledge some limitations of future work. We are currently only using one climate model. Our study does not include the impact of climate change on transmission, which has been shown to be larger and more significant. In literature, the impact of climate change on hydroelectric facilities estimated based on hydrological models. I use a simplified regression instead. And finally, we have only completed a limited number of Monte Carlo iterations so far, making our results a bit more noisy and less robust. However, on that note, we are planning on doing more iterations for the year 2040 and 2050. We plan on quantifying the impact to the grid's greenhouse gas intensity for increased peak demand and gas dispatching. And we'd also like to engage some key stakeholders in our research, such as the ISO, to further refine the model. Despite these limitations in future work, we do think that climate change will have an impact on our reserve margin and our loss of load expectation here in Ontario beyond what is currently estimated or planned for. Efforts should be made to incorporate climate modeling and forecasting variability into electricity planning. And although Ontario is planning on adding additional capacity in the future, it is important to consider the additional burden climate change may place on our grid. With that, I'll leave some time for questions. Thank you, everyone.
Nice job. That was very interesting. I'll start off the questions. Ontario is a very large area. I guess one question would be, is there one particular area of Ontario that's going to be hit the hardest? And then is there plans in the future to use this model for other regions throughout North America?
Yeah, so we actually broke down the ISO Ontario grid is separated into 10 different zones, and because it is very large. And obviously, demand will be affected differently in different zones. We see different penetrations of air conditioning use and all of that in each zone. And demand is probably the highest impact here with climate change. It jumps up a lot more than capacity dips down. So we will see different impacts that way. In terms of supply, it really depends on what is. So each zone has different types of generation. So the zones that have higher, as we saw, gas is most impacted. So whatever zones using mostly gas would be more impacted, especially in more southern regions where we're seeing potentially more spikes in extreme heat. So we will be looking at, I guess, zone specific impacts and diving into those as well in the future. So the answer is yes, I guess, the plan.
Great, thank you. Is there any other questions for Elise?
Hi, this is Narek. Should I just jump in or?
Yeah, go ahead.
Okay, great presentation. I had one follow-up question on the downscaling that you were using for the climate, I guess, future projections to the region. Can you just maybe speak to the precision of that downscaling, both from a geographical perspective, right? Because I guess, yes, Ontario is a large region, but climate sort of has much more macro effects, but also some micro effects. So how do you kind of think through that?
Yeah, so I can't speak. I didn't develop the climate model myself. It has been downscaled for higher resolution. I believe 10 by 10 kilometers for southern parts of Ontario, with northern parts being a little bit having less resolution. So, and each regression or model that I talked about has been applied with the climate for that specific generator. So we did I guess cluster generators as close together to like the weather stations, so that the weather variables feeding into the models were as close as possible to what was projected for that generator specific area. I don't know if that fully answers your question, but what we can do is we can connect afterwards. And if you're interested in getting more details on the specific downscaling, I can walk you through that with the person that developed the model.
Okay, great, thanks.
Looks like we have time for one more question. Eric, you want to ask your question?
Yes, thank you. Interesting talk. I don't know if this is important, but I just hearing that I got curious about this, and that is, are there important positive correlations between climate change and renewable generation? So if you have a heat wave, for example, it's probably not cloudy, so your solar panels are doing good. Or maybe with more of rainfall and sort of weather going on, that the capacity factor of wind plants go up, or you have more reservoir for your hydro. Is this something that's known? I'm not part of this area. Is this something that's well understood?
I would say probably not. So unfortunately, because of the uncertainty related with wind and solar radiation forecasting and climate modeling, we did not go the route of forecasting those types of variables and then feeding them into the modeling. So we don't know specifically with climate change what the specific impact and those correlations, like that is not happening in this type of modeling. It would be interesting to see, as you said, logically, that sounds correct, what you were saying, right? But we haven't actually put it to the test specifically here. So that would be something to definitely do in terms of renewables in the future, looking specifically at how they adding them to the modeling in terms of their impacts, if we can hopefully get more reliable climate modeling forecasts for those types of generators. So
thank you.
Great, thank you, Elise. That was very interesting. Our next presentation is going to be by Michael Craig. It's titled "The Effects of Climate Change on Capacity Expansion Decisions of Electricity Generation Fleet in the Southeast U.S." Dr. Michael Craig is Assistant Professor in Energy Systems in the School for Environmental and Sustainability at the University of Michigan. Michael, go ahead.
Great, thanks. You can see my screen okay? I take it and you can hear me okay?
Yep, looks good.
Excellent. All right, it's wonderful to be here. Thank you all for being here, and thanks, Branden, for organizing this. Also, thanks to Elise doing a lot of the heavy lifting I was going to have to do at the front of my presentation. Now I can just save all those 3 minutes for other things. My name is Michael Craig. I'm an assistant professor at the School for Environment and Sustainability. This paper was published this year in ESST, and actually Francisco is the first author on it. And this is a project that was many years in the making. Paulina Jaramillo was my advisor, and I worked on it with her as a PhD student, and it was funded by the NSF. So we're going to talk about climate change impacts on power systems. You will see some common themes and important differences with Elise. So first of all, just level setting, climate change, it's been happening. It's not some future thing that might happen to us. We have seen long-term global average temperature changes already, and we are not on path to hit 1.5 degrees Celsius. This is the UNEP budget report. Even if we were going to hit the 1.5 degrees Celsius target, we would still expect climate change to accelerate in the near term. All right, so climate change can have a lot of impacts on our meteorology and hydrology, and we can walk through how those affect different individual parts of the power system. And hopefully this is all just a refresher because of Elise. So we have things like increasing river temperatures, decreasing river levels, changes in wind and solar resources, and increases in air temperatures. And this is going to be in a United States context. So we can think about how each of these different changes in meteorology and hydrology will link to different parts of the power system. Thermal power plants, they use cooling, either dry cooling, once-through cooling. So changes in air temperatures as well as in hydrological conditions can affect your thermal power plants negatively, either through outages or deratings, meaning you have less capacity available. We can have changes in river temperatures, changes in river levels, both decrease the available generation from hydropower facilities. Of course, if wind and solar changes, we expect changes in wind and solar generation. And remember, solar farms, solar PV, loses efficiency at very high temperatures. So at high temperature extremes, we expect less solar generation. And then finally, increasing air temperatures, you run your AC more, demand increases. Okay, so our research is not about one of these arrows. There is a lot of research on each individual one of these arrows. Our contribution instead is thinking about the system level, just like Elise was previously. What we want to understand is if you plan a power system looking into the future and you plan it for climate change, how does that change your investment decisions then in a world in which you pretend like it doesn't exist? All right, so we're going to walk through a very simple schematic for what power system planning actually looks like. We have this bar, stacked color bars, and what is on the y-axis here is firm capacity. We want to buy enough resources, megawatts, gigawatts from different power plants so that our total firm capacity equals our peak demand, which is the black line here, plus some planning reserve margin just to be on the safe side. So this system is a well-planned system. You've got enough capacity to meet your planning reserve margin, and we've got some thermal power plants, some hydro, some wind, and a bunch of solar. So this is a high renewable system. And we can think about how climate change affects each of these individual components and then how it aggregates together into impacting your planning decisions. So first of all, climate change, pretty clear signal. It will reduce the available capacity of your thermal power plants. So we lose this little wedge in our maroon bars. Maybe we get a little bit less in summertime generation from our hydro. So we lose a little bit on the purple. Maybe we have very high air temperatures during our peak demand, so we get less solar resources, and we also get a small drop in wind resources. And finally, we get a big increase in peak demand. And there's a very consistent, robust signal that increasing air temperatures under climate change will really increase your peak demand on the order of 10%. So what happens if you do not plan for climate change? You pretend like it doesn't exist. What happens is you get into a future world where on the right-hand side, you have all the firm capacity after climate change has affected it, your demand increased, and so you have this gap here. And this gap is exactly what we do not want. This gap leads to things like Texas in the winter or like California last summer. And so we, as power system planners, desperately tried to avoid this situation. And so what our paper is going to do is take this very simple illustration that it could have made with crayons on a piece of paper and instead put it into a very fancy computational model to demonstrate, okay, how would our investment decisions actually change? So to quantify these impacts, what we are going to want to do is 3 different steps. First of all, we need high resolution weather and hydrological variables. We're going to generate them for a reference period, and then we're going to generate them for a future period. Like Elise, we're going to look at mid-century, except we're going to have 30 years in our analysis, and we're going to look at RCPs 4.5 and 8.5, although mid-century doesn't matter so much. We're then going to take these variables and translate them to changes in demand and on thermal capacity and on hydropower capacity. And we're going to do this hour by hour on a consistent synchronous basis. And finally, we're going to build a capacity expansion model. This is a long-term optimization model. It minimizes costs. And we're going to take that capacity expansion model and embed all these climate impacts into it so that we can run the capacity expansion model with and without climate impacts to understand how our investment decisions change. And so the red text here is kind of underscoring our main contributions here. One, we want a consistent framework for these different hourly changes. And two, most of the literature is just on those individual errors, temperature to demand, not thinking across a system. And so our main contribution here, I would say, is really looking at planning as a system under climate change. And for those of you who are skeptical that we even need this, just as a reminder, California last year, mid-August 2020, had what they called a heat storm, and they had rolling blackouts, 490,000 customers losing power for up to 150 minutes. And in their postmortem that the California ISO and other state government agencies wrote, they directly linked this event to climate change. And so whether climate change played a role in this specific extreme heat storm or in others in the future, this is, again, not something that is only happening in mid-century. These are impacts that are beginning to happen now and will only accelerate over time. All right, so we're going to stick to the eastern part of the continent, go downwards to the southeast United States, the CERC region, for those of you who love your NERC regions. We're going to subdivide it into 4 different areas: Tennessee, Kentucky, northern and southern Carolina, and then we've got the south there, Georgia, Mississippi, Alabama. And you can see this system is very heavily dominated by hydropower and by thermal power plants, coal, gas, and nuclear. And we've got a little chart for you here showing you is roughly a third gas, a third coal, and a third nuclear plus hydro. Very little renewables in this region as of 2017 when we took this data roughly. All right, so how are we going to do this? We're going to run a long chain of models. We're going to start at the very bottom, take global climate models, take that meteorological output. We're going to feed that into hydrological models, which are basically telling you how much water is in a river and how hot it is. And so we take climate data, we use it to force hydrological models, and then we're going to go from the meteorology and hydrology to the impacts on different parts of the power system. So given air temperatures, we're going to get demand. Given hydrology, we're going to look at hydropower. And given all the above, we're going to look at thermal capacity availability. And then, like I said, we're going to feed all that up into a capacity expansion model, a long-term optimization model, and we're going to embed time series from 3 different GCMs in there. And one limitation of this work is that we're going to use current wind and solar resources there. And so finally, we're going to run this capacity expansion model with and without climate change. And we're going to do that for RCP 4.5 and 8.5 to quantify your differences in your generator fleets in the future. All right, so we're going to start with looking at just what happens if we run for our historic case, reference case. No climate change, just plan the power system through 2050. You can see that what we do mainly is build a lot of natural gas and we build a decent amount of renewables. And this is just because their costs come down over time, so it makes sense to add wind and solar. Now we're going to layer on top of this climate change, RCP 4.5 and 8.5. One thing that should jump out is the number in the center of the circle. We go from roughly 140 gigawatts of capacity to about 200, partly because we decided to build a lot more solar, which has a lower capacity factor, partly because demand significantly increased, and to meet that increase in demand, we need to build more. You can also see, again, that we built a lot more solar. Instead of primarily investing in natural gas, we're going to have almost 40% of our installed fleet by solar. And so we see a shift if we account for climate change away from those thermal assets towards solar. Why do we shift our investment towards solar? Because it gives us generation when we need it. These are time series of generation for the different seasons in our capacity expansion model. And then at the end here, special is our peak demand period. And this dark orange is the solar. And so you can see in this peak demand period, we get a lot of really good generation from our solar power. Same in the summer, we get a lot of generation from solar during those peak demand periods. And you can see top row is under climate change, bottom row is no climate change. You can see this big difference in the summer, right? We get much more demand in the summer because of those increased temperatures. And we're going to use our solar power to make up a lot of that. Not thermal plants, because thermal plants are being curtailed or derated at the same time as we get that increase in peak demand. We can think of, okay, what if we put a carbon cap in? And so now we're going to look at climate change with a 50% carbon cap. And actually, this should look pretty similar. if we're planning for a carbon cap on the left, no climate change, we build a good amount of renewables. And then when we add climate change, we still see a very significant shift in our investments with climate change. So planning to mitigate climate change is not going to align your adaptation needs. And actually, we get a lot from adaptation in terms of mitigation. So we took those same plots that I showed you, where I'm just putting them top and bottom. At the top, we see our climate impacts. And when we plan for a climate future, we build a lot more solar, right? We saw that big wedge of solar increase into the future. And we actually build more solar when we plan to adapt to climate change than what we saw if we just try to meet a 50% carbon cap. And so in adapting to climate change, in meeting this 4.5 or 8.5 world, you actually are decarbonizing your system because it makes economic sense to, because of all the other impacts on thermal power plants. And so we see some synergies here between adaptation and mitigation. And we ran a stronger test case of an 80% cap, and we found roughly the same. You significantly increase your investments now, a lot more renewables. But again, we see the shift away from thermal power plants. So overall, what we found was if you plan for climate change, it does cause very significant changes in your investments. In our case, in the Southeast United States, we saw some impacts on thermal power plants. And so the model chooses to shift away from those and to meet some of that increase in peak demand with more renewables. And we see some overlap between mitigation and adaptation plans, which is good if you're a system planner. You don't have to do these either or, they can be both and. And one limitation here is that because of the difficulties of downscaling, we do not quantify changes in wind and solar power. And finally, given what's been happening in California, for instance, and given our research results, it suggests that current planners in the real world should really begin to incorporate these impacts, because while we and others run their analyses for mid-century, these are not just mid-century problems. These are problems that will increasingly happen in the near term. That's all we have. Thanks to the NSF for the funding and Exceed for computational resources. And I would love to answer any questions that you have.
Thanks, Michael. We have time for a couple questions. Does anyone have a question? Elise, go ahead.
Here we go. Let's hear it, Elise.
I put up the clapping hand sign, not the raise hand, but yeah.
Oh.
Give me a few seconds to think of a question. Someone else can ask a question.
Okay, sorry, Elise. Anyone else?
I have a question, if you can hear me.
Yep. Go ahead.
So your model seems fairly complex, and just based on your example of like California, I'm curious how you sort of pinpoint the main contribution to one set of results or another, so that you could maybe say like this effect has contribution X.
Yeah, our model is extremely complex. No, it's a great question. And that's the challenge of working with a model like this, disentangling the pieces. We actually have a subsequent paper that is currently in review. There's a working paper online now that I'm happy to send you if you email me. And we do exactly that we try to disentangle these different contributing factors. And in fact, in that paper, we don't just plan, we also operate the system and look for periods where demand exceeds supply. And so, yeah, there's a few different things here. You can look at the time series of increasing demand. You can look at the time series of increases in thermal deratings and hydropower changes. And then we go through a simple procedure to try to allocate resource scarcity according to each of those. And it's really a two-step process. You chose to not build enough, and so you can allocate some shortages there. And then given what you have, maybe you have some operational challenges, and so you can allocate there. But you're right, California would be, we did not analyze California. That would be a very different system just because they rely on a lot of different resources than we are capturing here. And snowpack, hydrology, very different out west than in our system.
Got it. Thank you so much.
Thanks. Dark. Hi.
Hey, Michael, nice presentation, and this makes a lot of sense and very timely work given all the catastrophes we've been having recently. So, one question I had was, and I'm a kind of a new person thinking about climate change impacts with respect to electricity systems. This is more just for me to understand better. So these climate projections, they're telling you average increase in ensembles of variables that are relevant for weather, right? But they're not really predicting extreme weather, right? If I understand correctly. So you will not be able to, for example, capture an event like what happened in Texas, sort of a week of intense cold, or do you? I'm just curious.
Right. So the global climate models are built not to do hourly extremes, right? They're built to project long-term averages.
Yep.
You're absolutely right. The purpose of a GCM and what it is best at is saying long-term changes in meteorology and precipitation, and some better than others. Like temperature, they do much better than precipitation. So then you get into all the downscaling procedures, and this team includes some hydrologists at the University of Washington who did the downscaling and the linking to the hydrological cycle. And that's where you try to get at some of these extremes. And so one way is like an analog approach where you take the historical record, whatever that distribution is, and you just move it. And so you still get that tail event. You might squash some of the tail being widened, but that's really in the downscaling is when you try to capture more of the extremes and the variability. And one of the reasons we don't do wind and solar resources here is because that is like, we had a 3-year project at NREL just on that, and that is like its own endeavor because of the difficulties associated with that.
Okay, so just on the demand side though, I mean, can you speak to how you're capturing perhaps the extremes on the demand side?
Yeah, so from the GCM, you get daily average temperatures. Demand or temperatures during the day follow a pretty regular diurnal cycle, and so you take that cycle and you apply it to the average temperature to take one data point and then put it over a 24-hour period. And the regression is trained not on historic data, but on that data that comes out of the downscaling for the historic and the future, because there's going to be some bias introduced in whatever process you do to disaggregate one data point into 24. And so you try to control for those biases as much as possible. But that is one of the things that people have been doing for a long time and they're very good at, of disaggregating one temperature value into 24, just based on that very regular diurnal cycle.
Thanks.
Thank you.
Sam, last question.
Oh, hey, Sam.
Hey, Michael, how's it going?
Hey.
Great talk.
Thanks.
I was just wondering if you could maybe unpack a little bit the differences you were seeing between RCP 4.5 and 8.5 with the capacity in particular, because I guess I would expect the increased demand from 8.5 to lead to more capacity in that scenario. So I was a little surprised to see the 4.5 was actually where the biggest capacity was. So maybe if you could unpack kind of what's going on under the hood, that'd be great.
Yeah, great. So Sam is pointing out that the middle circle 199 gigawatts is greater than 195, even though RCP 8.5 is the more extreme, like the maybe unrealistically extreme warming. And I would say this is largely just due to in mid-century, they look very, very similar. And so this is, in terms, you talk about a complex model, like there's just going to be some noise in the model and in the data that you input. And also, internal climate variability is over 30 years. And so how we are sampling across the 20 GCMs across 30 years for any given run, there's going to be some small deviations, and you always have to simplify in these large models. And so I look at that not as one is larger than the other, but basically by mid-century, all the meteorological changes are very similar. And so our results are similar across the two.
Awesome, thank you.
Cool, thank you. Thanks, Sam. Thanks, everybody.
Perfect. Thank you, Michael. Our next talk will be by Salma Elmala. Did I pronounce that correctly?
Yeah, you're good.
Perfect. Her talk is the gas to electric heating transition, electric infrastructure planning for residential building electrification in California. Salma is a PhD candidate in the Energy and Resources group at the University of California, Berkeley, as well as a graduate student researcher at Lawrence Berkeley Lab. Her dissertation focuses on the infrastructure planning and equity implications of California's residential gas to electric heating transition. It's all yours.
Cool, thanks. Can you see my slides?
Yes, it looks good.
Okay, sounds good. Thank you all for being here. So as Branden mentioned, I'm a PhD candidate at UC Berkeley. And I'm going to be presenting on some work on electric infrastructure planning as California transitions the residential buildings from gas to electric space and water heating. So My presentation and my work are broadly focused on building electrification, which is increasingly common in California and beyond as a climate change mitigation measure. And this work has a strong California focus, where electrification largely means transitioning gas burning homes to using electricity for space and water heating. And it's managed at multiple levels, as you can kind of see in these different screenshots. That includes utility rebates, state funding to incentivize all electric new construction. Some cities and counties have banned gas in new buildings or created rebate or incentive programs to transition existing buildings. So in California, this is a transition that's very much underway with the goal of reducing greenhouse gas emissions from buildings. And in California, buildings are the second largest emitter by sector after transportation. But there is also a broader context to this. Building electrification interventions are likely to become more common and are becoming more common in many states, where emissions from buildings are often the largest share of GHG emissions by sector. And so this figure kind of shows some of the states that attribute a lot of their emissions to buildings. And many of those states have committed to some form of decarbonization that would necessitate building electrification. And so studying these interventions becomes more important. So the work that I'm presenting on today focuses on grid planning and electrification. Intuitively, if we electrify buildings, it means that we'll use more electricity, and a lot of studies have started to address this. And so existing studies tend to focus on generation and transmission. Two of kind of these more detailed studies are noted here. One is from the National Renewable Energy Laboratory and another from Michael Waite and Vijay Modi. But on the distribution side, the work is a bit more limited. So we kind of see less of these detailed models that take into account spatial and temporal infrastructure data. And part of the reason for this is detailed by the National Renewable Energy Lab, or NREL, in this quote, which is that an assessment of distribution grid impacts is difficult because each system has unique characteristics and properties, which makes a lot of sense. And so this analysis really should be place-based. And some studies in California have done initial calculations, and they predict that electrification will shift the peak demand in California from the summer to the winter. And so maybe electric infrastructure will be more fully utilized as electrification becomes more common. But some of these studies do kind of acknowledge that infrastructure upgrades might need to happen, but the degree just depends on the location and timing of heating demands. And something that isn't reflected on this slide is that there is a growing body of literature that looks at how different distribution grids will have to change in response to climate change, in response to population shifts. And they do find spatial disparities in the quality of distribution infrastructure and in where upgrades would need to be targeted. So there is limited literature to build on with respect to heating electrification specifically, but there is a lot more work to build on with respect to different technologies and stressors that could impact electric distribution systems. And so the main question that this research addresses is where will electric distribution networks in Northern California require infrastructure upgrades to facilitate full residential electrification? And so in terms of Northern California, I'm focusing specifically on the area served by the utility Pacific Gas and Electric, where a lot of the interventions that I mentioned earlier, from like the city to the state to the utility measures, have been concentrated. So PG&E covers most of Northern California. There are parts of Northern California that are served by municipal utilities or other small utilities. It has 4 to 5 million gas and electric customers, and electric heating is increasingly common in this area, particularly in multifamily buildings. And so this project simulates 100% residential electrification, so a full transition from gas to electric heating. And this is an ambitious goal, but it is also a goal that's been set in climate action planning by municipalities as well as counties in this area. And so there are 3 key data sources that get at the variation in space and time that we're interested in. And again, PG&E refers to Pacific Gas and Electric. And so gas usage is made public by PG&E. It's reported at the zip code level, which is a fairly spatially resolved level for those of you who aren't in the United States. And it's reported monthly, and so that's a public data source. Distribution circuit limits are also made public by PG&E. And so this is a data source that's actually intended for developers and for solar installers to understand the grid limits of either installing load or generation technologies at different locations. And it's provided at a month-hour temporal scale. And it's kind of a data source that is intended for industry, but has been increasingly used by researchers, including researchers in my lab who've looked at kind of the spatial limits to integrating solar. But in my case, I'm looking at the load limits specifically as modeled by PG&E. And then to allocate heating demand throughout the year, I'm using hourly load shapes provided by the Department of Energy, the US Department of Energy, through the OpenEI program. And so these are simulated based on residential energy use surveys. And so there were kind of geospatial analysis methods used to reconcile these different spatial units and different temporal resolutions. But for now, I'll just introduce these data sources and jump into some results because of time limitations. Kind of the key takeaway here is that all of these data sources are spatially and temporally explicit to various degrees. And so that starts to give us some more specificity in understanding how gas demand maps to different distribution infrastructure limits. And so just jumping into some results. So figure A on the left here shows a map of results. And so the unit that's being mapped here is individual feeders, kind of drawn as the line segments of those feeders. And so a darker line indicates that infrastructure upgrades are needed or are needed to a greater degree. And for those of you who are familiar with California, the darker lines, many of them are kind of around the San Francisco Bay Area, which tends to be a more densely populated area. These gray shaded areas are regions that are outside of PG&E's service area. So these are often municipal utilities and we don't have data on their electric infrastructure. And this kind of tan brown is just here to give you a sense of the landscape. So these are mountain and forested areas that tend to be a bit less populated. And so this figure on the top right here shows the cumulative percent of feeders that would require different upgrades. So you can see that actually the vast majority of feeders, 80%, don't require any upgrade at all, but the other 20% do. And if we map this instead by the cumulative percent of populations served by those feeders, the curve shifts a little bit and it adds some context. So even though only 20% of feeders require upgrades, those feeders serve 40 to 50% of the population. So it kind of indicates that those feeders are concentrated in denser areas. And so the next few slides look at the feeders that require upgrades relative to the feeders that do not. And so figure 3A on the top left here. So what we mean by the month when the feeder is most constrained is kind of the month in which the feeder's capacity is most limited once you consider the additional electricity demand due to heating. And so the feeders that don't require upgrades, you can see that almost entirely they face constraints during the winter month of January, which kind of validates this conventional wisdom that heating electrification is going to shift demand to the winter. But feeders that do require upgrades kind of have more varied constraints. They tend to be more constrained in the winter, but there's some variability there. And so that might mean for the minority of feeders that are facing summer constraints, even in a situation with 100% electrification, they might kind of already be so constrained in the summer that shifting demand to the winter still isn't shifting when they face those constraints. Here, again, we're comparing feeders that don't require upgrades versus feeders that do. And so the y-axis shows an average predicted hourly load increase due to heating electrification. You can kind of think of this as proportional to gas usage. It's scaled by our assumed equipment efficiencies. And so locations with feeders that require upgrades also tend to serve households that use more gas overall, although there's quite a bit of variation in both cases. And here we're looking at circuit data. And so the y-axis looks at how much load can be integrated into each feeder now without, assuming a full electrification case. And so we find that the circuits that do need upgrades, if we do electrify 100% of homes, are already much more limited in terms of their average integration capacity. So they're already quite constrained. And this is kind of a different way of representing figures B and C. So we have the hourly load increase on the x-axis, and we've got the load integration capacity per feeder on the y-axis. And you can kind of see a clear division between the feeders that don't require upgrades and the feeders that do. Each dot represents a feeder, although there is kind of a clustering in the bottom left here. All right, I'm reaching the end of my time. So just quickly, kind of the conventional wisdom and back of envelope results that drive a lot of the analysis around distribution grids and electrification, especially in California, is that the demand is going to shift to the winter. Right now, the peak demand's in the summer, so we're all good for upgrades. But this analysis shows that circuit upgrades will be needed, especially in more populated regions. And it also raises a lot of questions and kind of follow-up work that I'm just going to leave here because of time constraints, but I'm happy to talk more about in Q&A. So thank you to you all for listening, and particularly to my colleague, Anna Brockway, and my advisor, Duncan Calloway, who worked a lot with this circuit integration data and offered really valuable guidance. And please do reach out if you want to follow up beyond this session. Thank you.
Thank you for that talk. That was very interesting. Michael, looks like you have a question.
Hey, yeah, that was really great. Thanks so much. I have two questions. One, well, not a question so much as we just talked for two presentations about increasing demand due to climate change in the summer. So I wonder how, like, if you combine these two analyses, you need to upgrade feeders for electrified heating in the winter, but you also might need them to do them for the summer. I think it'll be really interesting. My question is there any underlying pattern to which feeders need these and links to socioeconomic conditions, like new feeders that have been built in the last 10 years in suburban neighborhoods are fine or something like that?
That's a really, really good question. It's actually something that I want to look at in terms of future work, because I think there is a good amount of work, especially coming out of the University of Michigan, on disparities and like how much energy people use for heating and how there are kind of socioeconomic disparities in that. And I think, yeah, linking that to circuit upgrades would be really useful. Yeah, so it's definitely an area for future work. I don't have an answer for you right now, but I'd be happy to talk more once I've run that analysis.
Any other questions? All right. Thank you for your talk. That was super interesting, and it'll be interesting to see how it can be combined with Michael's and Elise's work maybe in the future to see if we can even out that grid load. All right, we have one last talk for this session. Last but not least, we have a co-hosted presentation by Isaac Bromley Delfano and Julian Flores. Isaac and Julian are third-year undergraduates at the University of Michigan studying electrical engineering and industrial and operations engineering, respectively. They share a passion for renewable energy and are deeply motivated by the global climate crisis and inequalities exacerbated by modern energy systems. This summer, Julian is conducting research at the Santa Fe Institute, and Isaac is interning at the National Renewable Energy Laboratory. Their talk is Reliability Benefits of Wide Area Renewable Energy Planning Across the Western United States. Isaac and Julian, go ahead when you're ready.
Awesome. I'm hoping to allow Julian to maybe control my screen as well. I don't know. I'm not seeing the same button. So if anyone has any advice on that, but if not, I can just click through. Sorry, Julian.
It's fine. I'll just say next when you move to the next.
Okay, sorry about that. Anyway.
Okay.
Hello, my name is Isaac Bromley Delfano, and I'm joined by my co-presenter Julian Flores, presenting our work on reliability benefits of wide area renewable planning across the Western United States. This research is conducted under Professor Michael Craig at the University of Michigan Asset Lab.
Okay, so this presentation, like Isaac mentioned, is looking at variable renewable energy, think mainly solar and wind in this case, and their respective impact on the grid. We use a metric called the effective load carrying capability, or the ELCC, which is just a way to measure the impact of the generator on the respective grid. And so it's not just looking at how much energy comes into the grid, but when that energy is coming onto the grid. So we're just going to be walking through a hypothetical scenario. visualizing this so the rest of the presentation actually makes sense. So this is the hypothetical load curve. You can see that peaks in the mid to late day. That's when everyone's using their energy appliances, and then it dies down when people go to bed. You have some type of standard capacity. Think of these as your conventional assets, your nuclear, coal, natural gas, something which you can turn on whenever you want them to be turned on. If you add a renewable generation source to this, or first, if you have any load that's greater than your capacity, that's a loss of load hours, like Elise was talking about. If you add a renewable generation source, in this case solar, you can see that you gain that additional capacity in the middle of the day. What that leads to is then you have a greater reliability with that generator and a smaller loss of load hours due to that additional capacity coming on. What we then want to do is we want to add this incremental load, this constant load, which is represented by that small blue line, which generates this new hypothetical load curve. And then we can run the same analysis over and over until we find that the new reliability is equal to the original reliability. And when that happens, that additional load, which is able to come onto the grid, divided by your nameplate, is your respective capacity value. All good. And then connecting to our study, you can see from the image on the left, the current status quo in terms of resource modeling and planning is quite fragmented. And where our study seems to answer what happens if you look at it more from a macro perspective. And that's where the wide area renewable planning comes from. And this, coupled with the increasing adoption of variable renewable energy, really paints an interesting research topic going forward.
I'm so sorry, Julian.
Okay, perfect.
Attention. All right, anyway, so I will now just go through our ELCC model, which really follows that definition that Julian provided. And the only thing I want to note, in case it wasn't already apparent, is that the ELCC quantifies the reliability contributions of a particular generator to a particular system. So it belongs not to the generator, but to a generator system pair. And so we begin with the system-specific features, including the demand, as well as the generating assets which we use to meet demand. And then we want to quantify reliability and answer how well does supply meet demand. And we do this stochastically using a non-sequential Monte Carlo state sampling method. Well, that's very buzzwordy. Really, we're just sampling outages in generators due to broken parts or supply chains. And this allows us to compare 5,000 sampled capacity curves with demand and quickly identify loss of load events and count those as well. And then to establish a baseline between systems, we adjust our fleet composition until we meet a target reliability of 1 outage day in 10 years, which is, as has been brought up, a very typical planning target. And then we add our hypothetical generator. We expect this to improve reliability. And we go through that last step in the ELCC calculation, where we add a constant load to every hour of the year until the new reliability with both the added generator as well as the added load is equal to the original target reliability. And in this presentation, we report ELCC as a percentage of the nameplate capacity of the added hypothetical generator. So this slide just shows the relationship between some of the key sources, inputs, and features incorporated into our model. So we pull from 3 main data sets: the IA860, which contains information on generating assets in the US, MERA, which is a NASA meteorological data set, and the IA930, which has balancing authority level load and interchange data. We pull storage, power, and charge capacities from the IA860 and dispatch storage to maximize reliability. We use generator type, capacity, and location information, as well as temperature data from MERA to incorporate temperature-dependent forced outage rates into our model. And insofar as we know, we are the first ELCC model to do so. And then using irradiance and wind speed data from MERA and the National Renewable Energy Lab System Advisor model, we simulate PV and wind generation profiles, which we use to account for both the existing solar and wind plants, as well as the generators for which we calculate ELCCs, and we get load and interchange from EIA 930. So as I mentioned, there are these 2 degrees of freedom within the ELCC metric, the generator and the system, and we want to conduct a comprehensive analysis of the Western United States, which fully explores both of these. So we partition the Western US into 5 power pools. And then for each individual power pool, say the Northwest Power System, we calculate the ELCC of a hypothetical 500 megawatt wind plant at the first MERA grid point. And then we move that wind plant to the next MERA grid point and calculate the ELCC contributing to the Northwest Power Pool there. And then we do this at every MERA grid point across the entire Western US until we built up an ELCC map for wind generators contributing to the Northwest Power Pool. And then we repeat this for each of our 5 power pools. Lastly, we test the sensitivity of our results to the year of meteorological data studied, the inclusion of temperature invariant or fixed forced outage rates as opposed to temperature dependent forced outage rates, the sensitivity to hybrid renewable storage deployments as opposed to renewable only deployments. And we consider the scenario where instead of 500 megawatts of renewable, deployment, we instead consider 100 or 2000 megawatts. So here's what one of those ELCC maps looks like. And this particular map is for wind generators contributing to the California power system. And just to reiterate, if we were to place a 500 megawatt wind plant at this point in Colorado and build it such that it could only contribute to the California power pool, what this slide shows is that the ELCC of this particular generator system pair is about 55%. And now for solar ELCCs, we notice a very distinct geographic trend where ELCCs increase from east to west. And this is pretty intuitive. Solar PV output peaks around midday, but demand doesn't peak until later in the afternoon, by which point the sun has moved farther west. So generators along the West Coast just make greater reliability contributions. As for wind ELCCs, they're much better correlated to average annual capacity factor or generation or wind speed. And as you can see, I think it was on that reference slide, these achieve ELCCs up to 55%.
Now we're interested in what is the impact of adding storage alongside that renewable device, like Isaac mentioned. So on your horizontal axis, that's just your initial ELCC, which is Isaac went over. And then on your vertical axis, that's the addition you get from adding a storage deployment. So the key takeaway from this is that when you have a low initial ELCC, you receive a much greater boost from that storage battery, versus if you have a higher initial ELCC, you still receive some type of boost, in this case 20%, but it's not as great as that low initial ELCC. So this trend continues. For solar, you still see boosts up to 30%, which is quite significant. And then moving on to wind, it's also quite significant as well. You're still seeing up to 30%. And what's quite interesting is if you get up to like 40, 50% with already initial ELCCs, you're still getting up to that 10, 15% boost. So now moving on to temperature dependent forced outage rates. Why is this important to begin with? You can, like Michael mentioned, Texas and California have recently been dealing with temperature correlated outages and then massive failures resulting from that. And so what this map represents is when you link temperature dependence with forced outage rates, you expect high temperatures in the mid to late day, which then leads to more generators going out, which then means any energy being able to come onto the grid at that specific point or time period leads to a greater increase in ELCC. And so that makes sense as solar comes onto the grid at that specific time point. This occurs across all the different regions, and it's heightened in the Northwest, but you still see an increase across regions. As you can see from these images, Basin still doesn't really get up to the same levels as the Northwest, and that's just due to the load generator matching pairs. With wind, it's not as consistent. You're actually seeing decreases in cases, and that's just due to the wind generation profiles not overlapping with that heightened risk time period. However, in certain cases, you do actually see an increase similar to solar, such as in the Northwest there. So in summary, and where is this project going from here? It's quite clear that wide area planning can deliver critical benefits, and we should be looking outside of one's own balancing authority. Storage serves almost as like a spatial flattener, where you see these respective increases in ELCC, especially for the lower initial ELCCs. And temperature invariant forced outage rates should be considered. That's something which we really haven't seen in resource modeling. Future research, as you can see from the image on the right, WEC is just one component of a very complex grid. So expanding this model outside of WEC could be very revealing and helpful moving forward. And also exploring climate change's effect, like Michael talked about, it will be playing a critical role moving forward in the future. And so thank you so much. These are some of the institutions and people which got us to this stage where we can present and talk about this great research. And thank you so much for listening. You can either ask us any questions right now or just email us at the email addresses below.
Great. Thank you so much, Isaac and Julian. I have one question to start off this question session. On the one slide that you had, the wind maps, it looked like there was high ELCC values off the coast of California. I don't know how feasible it is to put wind out there, but is that taken into account in this model somehow, how feasible it is to actually create a wind farm off the coast of California?
Yeah, I mean, so we actually do sort of neglect the offshore wind portion in our analyses. We just include that in these images. But I mean, that brings up a pretty good point that you're not going to build a solar plant on the top of the Rocky Mountains either. Yeah, so I think he was just trying to stick with that MERA data set resolution just so we can get a full geographic understanding. Yeah, so we don't address the feasibility of those projects at all.
Okay, is that something you're going to look into in the future?
Yeah, I think we are interested in that. And I mean, obviously we are not really taking into account economic considerations, social considerations, environmental considerations. I think wide area planning has a lot of consequences, especially as a result of the increased transmission that would be required. So I think those are all things that we'd like to look into and is a natural progression of this sort of strategy.
Perfect,
Yes, stay
thank you.
tuned. I think there's other projects in the pipeline dealing with that exact topic.
Awesome, thank you. Is there any other questions? Jethro?
Hi, thank you for your presentation. I really appreciated it. I had a question about the number of Monte Carlo runs you did. I think you picked 5,000, is that correct? Is there a reason why you picked 5,000? Do you think that's too low, or could it be a bit higher than that just to get a better distribution or capture the extremes at the high end and the low end?
Yeah, Julian, do you want that one? Or...
Yeah, I mean, we ran multiple tests looking at how many simulations do we actually get and what do those results reveal in terms of what are the ranges we're seeing. I think we came to agree that 5,000 was where we're not seeing that much variation. And that was, we also explored that exact question. But yeah.
Thanks.
Thank you.
Any other questions for Isaac and Julie? All right, I'm gonna take that as a no. So that was the last presentation for this session. Thank you to all the presenters that presented today. I think it was an extremely interesting session and had good correlation between the different talks. That is the last session of the day, I believe, for the ISSST portion.